reconnected. I think I went offline. Maybe back now. Internet hiccup. Moo says I'm back. Oh, hi. The internet. Technology. What's that like? Gosh. Right, okay. What am I doing? Oh, I was going to tell you another problem. Let's have a quick look at the list. Bracket quadratics. So the event I was at yesterday, Ben Green stood up, and Ben Green, instead of telling us really about experiences with Vicky or memories of Vicky, Ben Green just took a board pen, walked to the board and said, I just want to show you some theorems and conjectures from Vicky's thesis. It was brilliant. One thing that was involved seemed like the sort of thing we could explore. So I want to show you a topic I'd never heard of, and I've googled it. I can't. I googled it. I can't find anything about this topic. So if you can find anything, then you're helping me out. Here's the thing that's involved. So it's sort of classic result from number theory is that some numbers can be written as the sum of two squares. Brackets, and we know which. So this is a really good problem. Yeah, someone just walked past in the street. I'm not showing you the street because you'll work out where I live, but it's noisy out there, yeah. Okay, classic result from number theory. Some numbers can be written as the sum of two squares, and we know which ones. I'm not going to tell you which ones because it's a really good problem that you should investigate if you haven't seen it before. I don't know. It's possible I talked about it 3 weeks ago. Apparently, my memory does not work over that kind of time frame. In Vicky's thesis, Vicky Neal, what about a different sequence? So I should say people have thought about sums of squares and sums of cubes. How can you write sufficiently large numbers as the sum of 5 cubes or something, the sum of 10 fourth powers? And these involve different sequences. The square numbers, the cube numbers, the fourth power numbers, are classic results. Vicky managed to adapt some of the results to the sequence of numbers that works like this. And my understanding from what Ben Green told us yesterday, and I really want to find out more about this, is it works like this. You take your number n and you multiply it by root 2 and take the floor of that. So remember, floor rounds down to an integer. That's not how mathematicians actually say it, but it's how I think of it, so whatever. And then multiply by n, so there's a couple of times in here, I guess. And this sequence is a bit like the square numbers. If you make n twice as big, this bit gets twice as big, and this bit gets about twice as big, so it's about 4 times as large overall. But it's not the square numbers. And the floor function in the root 2 destroys a lot of the stuff that you would do in the proof. So it's non-trivial work to adapt from square numbers to these numbers. How does flooring work for negatives? We are going to do positive numbers only, probably. In general, flooring rounds down, so floor of minus pi is minus 4. The kind of technical definition, or the actual definition, is the floor of x is the largest non-negative. Sorry, the largest integer less than or equal to x. So floor of minus pi is minus 4. Okay. Hello, username pi. We are talking about some maths that Vicky Neal was interested in across different topics, and got a new sequence that I'd just like to explore. I don't think we're going to get to the stuff that is actually in Vicky Neal's thesis, but hey, I thought we could play with this sequence. My plan was to try and put it in Desmos and see what it's like, if that's all right. Let me just switch over to a Desmos window. There's a Desmos window. So the sequence is supposed to be, you take your number n, and you also take, hang on, let's make this a little bit smaller. Let's pop down to be that size. There we go. Take your number n or x or whatever. Can Desmos deal with n's? Not really, no. X, and you multiply it by the floor of square root 2 times x. Yeah, that looks good. I suppose I could put this on the whole numbers like this by asking Desmos to show me this for n equals 1, 2, 3, 50 or something. I need to do some sort of parametric thing so it knows what the x coordinate is. Bear with me, chat. Yeah. Yeah. Do I want negative numbers? Not certain I want negative numbers. Okay. So this is similar to, but not exactly square of x. The red dots are this sequence where you take like the number 3, you multiply it by root 2, n root 2 like that. Does that look better? Not really sure. N root 2. So 3 root 2, you take the largest integer that's smaller than 3 root 2, and then you multiply it by 3 again. And apparently 3 root 2 is a little bit bigger than 4, so the floor is 4, and this gives the number 12. That's not too bad. Do you want 0 in natural numbers? I think I want this for integers, but actually, yeah, if I'm making things out of the sums of these things, then adding 0 is... Oh no, adding 0 is fine. When you're building things out of 2 squares, people tend to count 0 as one of the squares. Is it obvious what happens for negative numbers? No. Okay, observation. Some of these are bang on. Is that bang on? Some of these are bang on, and some of them, the red dots are above the green line. Does that carry on? Does it keep doing that? I always forget about how I should feel. I'm a bit surprised that the red dots are above. Oh, I suppose I should be comparing to like x squared times root 2 and it's slightly below. Yeah. So it's kind of obviously below x squared times square root 2. Because it involves rounding down part of that this floor thing is always less than n root 2 or equal to. Maybe I should be comparing it like that. So somewhere in between. How fast does this grow? Looks like it's a bit bigger than x squared, but not as big as x squared root 2. But probably asymptotically it's about the same as x squared root 2. That's very close. Okay, not a good question. Ooh. Okay. Let's go back. So the theorem that Ben Green told us yesterday, I think I'm going to get this right. I hope I can. I haven't found a copy of Vicky's thesis to check this against, so I'm kind of going by memory. For any r, there is a number which can be written in the form n1 floor of root 2 n1 plus n2 floor of root 2 n2 in r different ways. So this is like the way sometimes there are multiple ways to write a number as the sum of two squares. If you'll allow 0 for a moment, then for example 5 squared plus 0 squared is the same thing as 3 squared plus 4 squared. Sometimes there might be lots of different ways. Maybe. I'm not actually certain. I said that as if it was obvious and then realised as I was saying it that it's not obvious and I've lost confidence. I have no idea why this fact at the bottom is true. I kind of want to find Vicky's thesis. I won't understand it at all because it uses, well, it's about number theory, which I know nothing about, and it uses really advanced techniques. Of course it does. N without N is the number 0. Sorry, I have been ignoring chat a little bit because, well, I typed a 0 and then that's the only thing that's been going on in chat for a while. Are people aware of this maths at the top? The two squares thing. Do a tiny bit of that. Let's do a tiny flavour of that just for people who haven't seen it before. It's a good problem, which you should think about. So I've got some numbers. So 1 is the sum of two squares. And then there are some more numbers. Let's try and lay this out neatly. 2, 3, space, 4, 5, 6, 7, suspiciously 0 over here is the sum of two squares. And then 8, 9, 10, 11, 12, 13, 14, 15. So the sort of thing that I might have talked about before on Oxford Online Maths Club or something. 2 is the sum of two squares because it's 1 squared plus 1 squared, because 1 plus 1 is 2, and so on. So this is which numbers are the sum of two squares, and squares could be 0 and could be the same. I would say two distinct squares if I needed them to be different. For example, 8 is 2 squared plus 2 squared. That's fine. Maths Club episode where all the numbers of 100 were written out. Yeah, there's something with complex numbers in here because maybe the sum of two squares is the modulus of the complex number AB, right? So if you have a complex number a plus bi, where those things are both whole numbers, then the modulus of a plus bi by Pythagoras or something is a squared plus b squared, or the modulus squared is a squared plus b squared. Larou's never seen Maths Club. Yeah, mod 8 comes into it somewhere. Squares are just nice mod 8, in my opinion. So mod 8, by the way, means the remainder when you divide by 8. It's why I've tried really hard to have 8 columns here, in case somebody is copying this down to do it at home. 8 is just nice. Can I show you some squares, mod 8? So mod 8, again, ignoring multiples of 8. Here are some numbers. And these are the only remainders that you might have when dividing by 8. And then let's talk about x squared remainder when you divide by 8. And if your number was a multiple of 8, then its square is a multiple of 8. If it was one more than a multiple of 8, then algebra 8n plus 8k plus 1 squared is 64k squared plus 2 times 8 times k plus 1. But it's one more than a multiple of 8. And the more you do this sort of thing, the more you realise that it works quite nicely and remainders can't carry over. So 3 squared is 9, which is the same thing as having a remainder of 1. You're allowed to do this thing where you just square the number and then take the remainder, rather than considering all possible things that would have the remainder, squaring all of them and checking that they will have the same remainder afterwards. That's not obvious. worth checking. If you square a multiple of, if you square something that's 4 more than a multiple of 8, you get something that's 16 more than a multiple of 8, which is a multiple of 8. And then 5 down here. The squares then go, I think, backwards. 5 squared is 25 is 1 more, 36, but this is a bit like 2 less. So anyway, there's just not that very many things that your square can be. So this is pretty nice. Vicky has done some maths where you factorise an expression with complex numbers. There's this amazing relationship that, let me show you, which I learned from a Vicky Neal talk, which is you're working on these numbers trying to make products. And there's this amazing thing that a squared plus b squared times c squared plus d squared. So if you have two numbers that can each be written as the sum of two squares, if p and q can each be written as the sum of two squares, which I'm going to write as SOT's sum of two squares, then PQ can, and the proof looks like this, that it is AC minus BD squared plus a Vicky would do this so fast. Is this expand and check, but the real proof is slightly better, and this is the other thing we've been talking about. The other thing we've been talking about is how you can have multiple methods or multiple proofs or multiple explanations, and maybe if you've done a lot of work to actually expand that and check it's true, then you're not very satisfied because there's something going on underneath, which is that this is the modulus of z1 and the modulus of z2, and the modulus of z1 z2 is the same thing as modulus of z1 and modulus of z2. So then it follows through. You can square both sides. And on the left there, we've got the modulus of z1 squared and the modulus of z2 squared. And on the right, we've got the modulus of the product of z1, z2. All we need to do is work out the product. And working out the product involves, in your head, working out how to multiply, remembering how to multiply complex numbers, which is always the hard bit for me. There we go. Gives you the right-hand side. Delicious complex numbers. Is it AD minus BC? Have I screwed up? My current opinion is that I have not screwed up. You can flip both signs, I think. I think you can flip both signs and everything's fine. You need the cross term to vanish. Is this true? Oh, you were talking about the determinant of a 2 by 2 matrix. Sorry, yes. That's the thing that comes up a lot, isn't it? Neural activation matrix data. Oh, sorry, yeah. Is that matrix multiplication? Is that the same thing, morally? The determinant secretly something to do with... is the determinant of a 2 by 2 matrix secretly the product of complex numbers? Yes. I think it is. Let's see if we can justify that. See if we can make that real. Linking via determinant being the area of the transformation of the unit square. Yeah. Yeah, it is close. It is close. We're almost there. I can't quite see how to pull out the real part, make it have something to do with the real part. But the thing I'm imagining is this relationship to bring some matrices in. So this is the proof done. But to bring some matrices in, you can imagine a matrix in general like this, which is not quite the one that I wanted. Yeah, whatever. Whatever, it's almost there. you can imagine this matrix as representing the way it acts on this vector is to send it to AB, and the way it acts on this vector is to send it to CD. Now, if you interpret all your vectors as complex numbers, then this matrix is sending complex numbers to complex numbers, and in particular, it's sending the unit square to a sort of parallelogram with corners here and here, which are A plus BI and C plus DI. The determinant of the matrix gives the area of the parallelogram. That's not obvious. That's not obvious. Yeah, you shouldn't let me say that. Not obvious at all. Can I do a link up between the other two things? I'm sort of bailing on this explanation because I've realised that I'm just free associating on random bits of matrix algebra I remember, which is not helpful. If you'll let me equate vectors and complex numbers and matrices to maps of complex numbers, then there's a nice link between all of these things. Do you know the link between matrices and Fibonacci numbers? Just to bring us all closed loop, bring it all back together. We've got diverted onto matrices, so let's get back on track by getting back to Fibonacci numbers. No? Yeah? What's this? Yeah, okay, let's do. I would like to know now. I'm going to assume that they're talking to me about the thing that I'm talking about. Yeah, cool. Okay, I'm interested in Fibonacci numbers. Works like this. I should always plan these things because they have a tendency to just blow up and go wrong. It's very hard to do it in my head first. What the heck? Let's just see what happens. So I think if you take powers of this matrix, now power of matrix means, so this means times 1101 times 1101 times, yeah, and this is a terrible idea. I'm really committing to it being exactly this matrix that I want. Then something nice happens. No, I've messed up. I have messed up. AB gives me A plus B, and it gives me B. Is that what I wanted? And it'll give me, add the components. I want to show the top one. Yeah, I want the one to be over here. I hard committed incorrectly. Okay, power of matrix always means just multiply together that many copies of it. And I think this one's good. Let's do some matrix multiplication to find out. So 1110 times 1110 is, matrix multiplication says read along the rows down the columns, 2, 1, 1, 1. And then multiply it again. Should I do this on the left or the right? Does not matter. 3, 2, 2, 1. I think it's working. We've built a machine and it's off and away. And the question is, will it keep working? 5, 3, 3, 2. Yeah, it's working. The machine is doing the thing that I wanted it to. So as you keep multiplying these matrices together, looking down a lot to make sure I don't mess up, 8, 5, 5, 3. You get this nice sequence coming out of the matrices. And I guess at university you learn these, you learn some methods. There exists a nicer method for this. The way I'm doing it by just multiplying matrices together again and again is kind of the slowest possible way of finding your matrix powers, and there are some good accelerations you can do. Yeah, if you know about matrix diagonalization, you should go and do that. Diagonalizing your matrix is really good. The reason being that if your matrix is just diagonal, then the powers work really nicely. It's just not very much maths to do. If you can diagonalize your matrix, then the power of that is just p d to the n, p inverse, by the p's cancelling with the p inverses when you do the power. So everything's quite nice. Diagonalizing it is the thing I'm referring to make it faster. And I think when you learn this at university, then diagonalize your matrix and now do powers, it's sort of its own thing. It's got lots of applications, but my favourite is it lets you do recursion relations really nicely. I want to tell you a little bit more because I think this is cool, but I can go slightly better to show you how to build your favourite recursion relation out of matrix powers. Yeah, there's something to do at home. Something to do at home here, but the link between these things and recursion is. So what do you actually need for the Fibonacci numbers? For the Fibonacci numbers, you need to keep track of. So Fib says keep track of the previous two numbers. You'll need both of those, and then the operation you do, I would describe as add the numbers. But if you only need the previous two numbers for the further calculation, then you can throw away the smaller one. Now, one way to imagine that is to make sure you keep the larger one in the same place. You work out the next one and then slide everything down by one. So you kind of want to go from in storage. In storage you had AB, and then you want to go up to A plus B, A. So you want to take your two numbers that you've got and not only add them together, but remember to keep this A thing and throw away the smaller one. So you want to go from here to here, and that's a linear transformation. The thing that I was trying to remember and screwed up slightly is the matrix that does this. The matrix that transforms vectors like this, vector AB to vector A plus BA, is 1, 1, 1, 0. This top row says take the components of your vector and add them together, A plus B. And the bottom row says just show me the first component, throw away the second component, A. So you can use your matrix coefficients to express these rules, both the sort of rule where you add together some stuff, and also the sort of rule where you throw some numbers away and just take one of the previous things you had. So you could do adding 3 numbers. My favourite sequence at the moment would be something like you want to add the 3 numbers together and then do a shift. So the thing that was at the top before should now appear in the second row, and the thing that was second should now appear. The thing that was second should now appear at the bottom row. So the bottom row here is going to read out the second number. So you do powers of that, you should get my favourite sequence. Popping off the diagonals, I guess, probably. Slight further question as to why one of these columns is ahead of the other if you track the matrix, but you know, there's a little dance going on there. And then if you really care about it, you can do the sort of n-dimensional matrix, find the eigenvalues to work out the growth rate, which is that thing I was talking about with the growth rate before. But this works for a variety of sequences. So you might have a sequence which is like double the previous term and add 10 times the term before last. And that's fine, that's just some sort of like 2, 10, 1, 0 sort of operation on the numbers that you've got in storage. You take your numbers and you do something like, okay, you do some adding, twice of that, 10 times that, got it mate, and shuffle this, so this will return the A, the top coefficient, in the second position afterwards. Let's kind of, yeah, shuffling around. Oh yeah, initial values, you change the initial vector. Yeah, I agree. LaRue's and potatoes. Yeah, n numbers around here, you can keep going, yeah. So to get to n numbers, so long as it's a kind of fixed relationship that's linear in your previous data, then you can do matrix operations like this. Yes, I would do, yeah. So non-homogeneous recurrence relations, I think it does not work for. In fact, the only things that this works for are basically the things on the board at the moment. So things where you're doing a linear combination of a fixed number of the previous terms. If you're doing something more funky, like adds together all of the previous terms, no matter how many there are, or multiply them, or square some of them, or even add them but then subtract 3, so that's the constant 3, which I think is the kind of non-homogeneous stuff you learn about at school. So you sometimes see stuff like this, which is the same thing as saying 2 minus an or something. So you've got this kind of linear relationship between an plus 1 and an, except the 2's there. Yeah, so there is something I'm hiding a little bit. I'm hiding a little bit because it was so pretty that the Fibonacci numbers came out of here. I'm hiding the kind of starting value that I'm imagining. I'm imagining this matrix being applied to the starting initial condition 1, 0 or something. That's a little bit sneaky because you can see with your eyes that there are Fibonacci numbers here. How do you actually get them out of the matrix? It's not that hard. You need to act that matrix on your values. So the thing we've been doing all along is something like this, or whatever your starting values are. Yeah, m to the n can have all of its own special transformation that we can apply to vector to Fibonacciize it. Yeah. There's this lovely result that I saw Vicky talk about in a very short video on our social media channels, that you can use the Fibonacci numbers to approximate the conversion rate between miles and kilometers, because the ratio tends to the golden ratio. And so the sort of best way to prove that, I think, is to look at the eigenvalues of this matrix. The eigenvalues give you the kind of growth rate. That's really, they tell you so much more than the kind of growth rate, but the real part of the largest real part of the eigenvalues gives you the kind of growth rate of the sequence. I'm erasing that in case any mathematicians see it. Yeah, okay, we managed to get it back to Fibonacci numbers, so that's good. I think Vicky quite likes the Fibonacci numbers. If not, then she talked about them enthusiastically a lot, and that's almost the same thing. She also, we've seen, set a puzzle of the day for which the answer was the Fibonacci numbers. It's nice to see them turn up in different places. Yeah, he doesn't like Fibonacci numbers. Right, okay. I haven't done the double number circle thing yet. I haven't done any perfect numbers for Zoe. Sort of want to let Zoe have a little chance to talk about complex. So talk about complex numbers. I don't know why I'm putting Zoe on the spot. Zoe said you explored something earlier. If you're still here, you said you explored something today. Wouldn't mind talking about that. Yeah, so the eigenvalues are phi and phi cognate. There's the kind of conjugate value. Wolfram Alpha can tell you eigenvalues. We've got a method for that, but yeah, the eigenvalues are something like, so the eigenvalues of the 1, 1, 1, 0 matrix are something like 1 plus or minus root 5 over 2. Which means that the growth rate is, well, the sequence that you get out of the Fibonacci numbers grows like 1 plus root 5 over 2 to the end. There's a fact about Fibonacci numbers which brings us back to the floor function, that you do something like you take this divided by root 5 maybe, and you take the floor, which looks a bit mad to me because there's the floor function ever involved in these things. But it's because there's a Clyde form exact formula, no rounding down, that involves both of these numbers, which I can't quite remember, and I might try and work out. Closed form formula for Fibonacci numbers? Nobody? Yeah, I'll have a go. Yeah, so it's something like, I can't remember the coefficients, but it's something like this, I think. And then the trick is to make sure that n equals 0 and n equals 1 actually work. So n equals 0 tells me that I should set a plus b to be 1, and n equals 1 tells me that I should set a minus b times root 5 over 2 to be 1. So I guess that means, oh, I don't love that. Yeah, that's happening though, I think that's happening. So a minus b is 2 over root 5. Can I set this to be 0 instead? That might be more fun. Yeah, that'll be more fun. If I start counting my Fibonacci numbers from 0, I think everything's nicer. Link wasn't deleted for me, but I'll try opening your link. Oh yeah, okay. So this is going to use the general formula, right? Ugh. It's loading the equations very slowly. I think my internet might be a bit weird. Oh yeah, okay. There's a lot of maths going on there involving generating functions, which I'm avoiding, I guess, out of cowardliness. Which I think gives me this formula. I haven't told you where these numbers, how to get from this matrix to these numbers, but maybe that's a price on. Maybe that's something I should have done. Yeah, that's quite good. Big if true, right? Big if true. Oh, mobile Twitch, it just says link deleted. I will show the link on chat. I can put it on stream, right? Just quick preview. Yep, preview's good. Cut it. Mathonline.wikidot.com. That's a lot of dots. The word wikidot. Slash a closed form of the Fibonacci sequence with dashes between words. But I guess maybe you googled closed form Fibonacci. This is quite an advanced technique where, oh my goodness, imagine that the Fibonacci numbers are the coefficients of an infinite sequence, and then try and work out what that is. That's cool. That's really cool. The sequence does be very nice as well. So this is excellent. It uses a version of that the thing you do for the geometric to prove that a geometric series converges. It's not a geometric series, but you do something pretty similar. That is very good. Consider the polynomial 1 minus x minus x squared. Partial fractions. This is quite good A-level content in a way. People in year 13 pay attention to this maths. If you search for a closed form of the Fibonacci sequence Math Online, then you could be reading about an infinite polynomial, an infinite series, like a very big polynomial, some weird summations, a cool trick, partial fractions, Fibonacci. Oh yes, I've got the right number of things. Good, okay. And we're back. You just found it on Google, yeah, that's fine. I'm going to try putting it in chat. If I put it in chat, does it get deleted? Don't get any privileges. Galactic Nova says that I should put this on Matt 2024. I think we did Fibonacci numbers this year. I'm not really allowed to do partial fractions, I think. Not really allowed to do partial fractions. Probably shouldn't do an infinite series that's not a geometric series, although we have done that. Yeah, it doesn't look like a root 5. Ha! I have link privileges. Amazing. So this being the Fibonacci numbers is ridiculous. You probably shouldn't accept it. I got quite cross when I was younger and someone just told me this and didn't give me any explanation at all, and I've kind of done the same mistake here by not really giving you any idea about what this matrix has to do with these numbers. I'm not going to. Yeah, okay. So it is. This matrix is equal to, and there is a good reason for this. There's some calculation you do. Is equal to this for some m, and m is horrible, and I don't want to tell you what's in it, but it's not important. The point is that if you're doing these powers, then really all you're doing is you're doing m this matrix, m inverse, lots of times. And if you write that out lots of times, the m inverses all cancel with the m's to leave you with just the nth power of that diagonal matrix. Multiplying a diagonal matrix by itself is really easy. So that's kind of where these nth powers of these numbers come from. And then the root 5 comes from some of this m horribleness. Is that true? That's true enough. True enough. We're not getting past those m's without some root 5s, I think. So yeah, it's bizarre. It's not at all clear that it gives you whole numbers. It's quite fun to try multiplying it out, actually, just binomial theorem it. Well, one way to write this is 1 plus root 5 to the n plus 1 minus root 5 to the n over 2 to the n root 5. And then there are kind of two surprises. One, that the root 5s go away, and separately that the 2's go away. So if like n equals 3 or something, this is 1 plus 3 root 5 plus 3 root 5 squared plus root 5 cubed plus 1 minus 3 root 5 plus 3 root 5 squared minus root 5 cubed divided by 2 cubed root 5. And something's gone horribly wrong, but that's okay, we can fix it. Did I want a minus all the way through? I did, didn't I? Oops. B is negative A. Oops. And this is lovely, because the root 5 terms cancel out. The root 5s all cancel at the top. You see that the ones that are just there root 5s, like this through root 5, cancel because the minus signs come to the rescue. This minus sign in here. And the ones that are on every even numbered term, well, that root 5 squared all raised to the power of 4 or 6 or 8, so that's just whole number. And then the next kind of surprise, I suppose. So, yeah, no, I've just said exactly the wrong thing, haven't I? Because of the minus sign, which I missed. Rewind. Take 2. The terms with a bare root 5 in just get added together. And these terms where the root 5 is squared, and they scare me because we're going to divide by root 5, they cancel because of the big minus sign in between. This is 1 minus 1, 3 root 5 plus another 3 root 5. So what we're left with is something like this, where it's every odd term on the top, so the root 5s are going to be fine. And then maybe surprisingly, the top really is a multiple of 8. This turns out to be the number 6 plus 10 is 16, divided by 8 is 2. And this is the stupidest way ever of working out the Fibonacci number that comes after 1 and 1. You know a much better way of working out the Fibonacci number that comes after 1 and 1. It's 2, because 1 plus 1 is 2. Yeah, something about even and odd things cancelling. People in chat are talking about learning matrix diagonalization. Matrix diagonalization is really good partly because of powers. Other reasons as well. Those things in the diagonal are the eigenvalues. It's sort of the right frame of reference to look at your matrix in. Doesn't mean anything, does it? If you can diagonalize your matrix, then sort of just acting on particular vectors in a friendly way. Can we use the identity of 1 plus 1 is 2? Yeah, alright, okay, good. Maybe only if you derive it. Wow! This is not a proof that 1 plus 1 is 2. Don't worry. Okay. I'm still messing around on Fibonacci numbers. Seems like I got a bit stuck on Fibonacci numbers. I'm going to show you one cool thing that I saw yesterday, which is Shabby's t-shirt. So someone who worked with Vicky Neal on the Enrich website stood up and, just like Ben Green, instead of telling us about interactions that they had with Vicky or how they met Vicky or something like that, they talked about a maths problem and got us to work on it because that's what Vicky would have done. So I want to show you the maths problem now. and it's got a nice easy link to find. So I'll put the link in chat as well. It's on Enrich. Toast potatoes, that is fantastic. Well done. Excellent banter. I'm sure it's come up on questions. How dare you? Right, so the problem is called Jaffy's t-shirt. So here's a t-shirt. Ooh, how do I show you the t-shirt? Oh, I am already showing you the t-shirt. Good. Which has got lots of circles on. And there's a clean version down here. Which I'm going to make nice and large. There we go. And the question is, what's going on with this t-shirt? So there's a rule for what's going on. I'm going to give you, like Vicky would always do, I'm going to give you 2 minutes to talk to each other in chat. What do you think is going on with this t-shirt design? I'm also muting myself, and I'm going to do something slightly different. And I'm really interested in what we're doing. Chat's doing great work so far. I forgot to set a timer. I've got no idea how long 2 minutes is. I'm going to drink some water. So the hydration alert, just because I want to get the water. Yeah, okay, get the water, drink the water. Chat seems happy. Let's have a chat with chat. Oh. Also coordinating. Something else going on at the same time. Have you worked out? So people are telling me about primes. People are telling me about primes, which I like. The exact colours aren't important. In fact, I have a button to shuffle the colours. If these are not good colours for you, then the website comes with this button in the corner, new colour, to shuffle it. Right, what are you telling me? So you're telling me the primes have got, Laruba put an empty circle where one should be. You're telling me the primes have got colours, and you're correct. Let me hover over some primes. 2, 3, 5, 7, 11. Those have got colours. But have you told me about composite numbers or everything else? No, I don't think people have. Oh, red is multiples of 5. Oh, okay. So the multiples of 5, 15, 25, 35, 45, and over here 5, 10, 30, 40. They've got a bit of red in them. Oh, you can't see my mouse when we hover. Bother. 2 seconds. Thank you, Lorud. That's a Twitch thing. No, it's an OBS setting. There we go. Here. Capture method. No, it's on capture cursor. Why is it not capturing my cursor? Whoa, I broke it. Now can you see my cursor? No, I broke it. Gonna fix that for 2 seconds. You can't see my cursor. Oh no, I ruined everything. Off and on again. Nope, can't fix that. Right, we're back. I've learned not to play with that setting. Can I do like a sticky keys thing? Oh, whatever. Multiples of 5 down the middle. Woomph. I can't see what I'm pointing. Composite numbers. People are telling me about composite numbers. A segment is a power of that prime. We're getting there, right? So we've got some ideas that this 10 over here, oh gosh, this 10 in the top right corner is red and green because it's partly 2 and partly 5. Very annoying, you can't see my cursor. The colours represent the primes. Each number is represented the product of its primes, with the colours representing the primes. Yep. And the colours within the splits represent the different prime factors. The same colour is used for the same prime factors. Yeah. And I'm sure if I put you on the spot and said, you know, over here, I can't see, down that right-hand column, you can see the first one split in 2, and the next one split in 3, with more green than red. I think you do have an idea for why there's more green than red in 20 than there is in 10. There's no point in me hovering, they cannot see. Yeah, it's got kind of more 2s in it. Okay, so this website comes with a sort of game, which is they show you a small amount of the grid with different colours, and the idea is to work out which bit of the grid you're looking at. Or is it? Oh, okay. It made this look so easy. Do I want this scarf? Oh no, I want a t-shirt. Here we go. In here? Window, yeah, window. Reload. Yeah, so game time. They show you a chunk of the grid. So this is a section of the t-shirt we were just looking at, but with new colours. So the colours don't mean anything compared to the colours we had before. The colours are randomised every time I press the button. Sorry, that's horrible, isn't it? There's my cursor. Now it's here. Where did it? Oh, never mind. And the game is to work out which bit of the t-shirt we're looking at in terms of what we're doing. There's some algebra, right? But some of the algebra is easy and some of the algebra is hard. So, for example, here we've got a prime and another prime, and they differ by 10. That's quite hard algebra. Over here, I can see some of the prime factors of this number are shared with this number, which is 9 more. And some of the prime factors are shared with this number, which is 10 more. So, gosh, there's something going on. You can give them names. So dark green being A, being a prime, is kind of interesting, but there's no more dark green, so it's sort of hard to link that together. So, gosh, how do you solve these then? Ways to solve this, there's got to be something like the attack has got to be something like this is yellow above yellow. These numbers are both multiples of the same prime, and they differ by 10. Blue is probably 3, because yellow must be 2. Could purple be 2? No, because then it would divide these as well, probably. Could yellow be 2? No, so some of these numbers are even. Maybe it's the middle ones. Yeah, it's not the outside ones. Okay, yellow is 2, and then you're getting somewhere, because this is 2 times a cube. That's not. So it could be 2 times 3 cubed. 3, 9, 27. It could be 2 times 27. Could it be 2 times 5 cubed? No. So I think that is 2 times 3 cubed. So I think that's 54. Yeah, okay, I'm with a cool person. Am I crashing? Am I still crashing? Oh no. Oh, I'll be gone in a minute for good. New viewers are getting pre-roll ads again, but that's alright. Okay, I think I'll agree that's 54. And then that would be 53, 43. 44 is multiple of 4 and 11. That all sounds good. That would be 55. Good, okay. And you can do a whole bunch of these with different grids. Enrich have built this website so that you can do this with different bits of the t-shirts, your favourite colours, and they have, as well as windows, they have zigzag like this, which is a harder game mode where you get just 4 of the things, and you have to work out where you are. this one's like quite a few primes, and then a multiple of that prime. So I reckon we're at the 2, 3, 13, 14 bit of the t-shirt. Yay! Hooray! Primes, and then things that are like, oh gosh, and that's blue shared there, sounds like the 2, and then the yellows are shared as well, even though it's 12 more, so, you know, good stuff. I think, I don't know a proof that you can work it out from a window of these circles like this. I think Enrich must have thought about this before they built the website. My suspicion is that they're giving you enough information to play the game. If there's just one circle, you can't work it out. Observation. So somebody's asked the same question as me, actually. So my question was, are we using the restriction that is on the t-shirt? The t-shirt's finite, and the t-shirt's finite. So there's only a few cases to check, right? Are we using that constraint? Or are we playing on some sort of imaginary, infinitely vertical t-shirt that keeps going, extra long, with all of the numbers on? And then I realised that that version of the game is very, very hard. For example, if you just see, I zoom, sort of. Can I zoom and just have those two? No, I've messed everything up. Sorry, Enrich. Excuse me. If you could only see a circle above a circle, prime above a prime, primes that differ by 10, nobody knows if there are infinitely many of those. So it'd be extremely hard to say anything about this puzzle in general on an extra long t-shirt. If the t-shirt went forever, you could never figure it out. So then the question is, are there any patterns where you can figure out what's going on? And the answer to that is yes, because if you see two primes next to each other, which we have before, I should have been faster on that one, shouldn't I? With a 2, 3, whatever it was, 2, 3, down to 13, 14. I should have been faster because there are two primes next to each other, which only happens at the top of the t-shirt. Back up to the t-shirt. And I think it is a real t-shirt. I don't know if you can purchase this. I can't see a link anyway. Can I go to Explorer or something? Yes, full. There we go. So there exist arbitrarily hard versions of the t-shirt problem, of the t-shirt. The other one that Charlie Gildale asked us yesterday was, how many of those circles are split in 5? How many of them are split in 6? What's going on there? And that's very hard as well to work out in general. Yeah, so circle, gap, circle is the twin prime conjecture. Does that appear infinitely often on an extremely long t-shirt? You can kind of see the twin primes on here. Cursor? Oh, I now have a cursor, great. Here's some twin primes. These are two circles that differ by 2. They're kind of pretty, right? There's some circles there. You never see any jumping over to here. And you get some of them over here, like here to here. And you can't quite see them on this t-shirt, but there's some wraparound ones, like 29 wraps around to 31 twin primes. You can visualize quite a lot of twin primes. Nobody knows if there are infinitely many twin primes. Nobody knows if there are infinitely many twin primes that aren't 1 more and 1 less than 1 more 10, because nobody knows, I think. Good. Okay, so this is a fun puzzle that people showed us yesterday. And it's that fun of exploring and messing around with it. There's also a scarf version, which I haven't said anything about, but I scrolled down slightly to show you this, which is, the scarf has all the numbers in a straight line, which is, all the numbers in a straight line, which gets around that kind of wrapping around problem, where sometimes it wraps around and there's this multiple of 10 thing going on. On the scarf, everything would just be in a kind of straight line, so you don't have to think about multiples of 10 quite so much. And then the fun part of this as well was watching a room full of people who knew Vicky and worked with Vicky trying out this problem, and seeing Ben Green, famous number theory person, pointing at it and sort of probably talking to people around him about subsequences in the prime numbers and things. I imagine. Very cool room. Oh, there's a conjecture that there are infinite Milling primes that differ by at most 12. That would be good. But wait, even if that's true, it could still be true that they mostly differ by 8 or something. Even that wouldn't be enough for me to do the t-shirt problem of the advanced t-shirt problem of here's a circle above a circle. Does that appear infinitely often on Shaver's massively long version t-shirt? Easy 90 marks. What's that? What's that for? Good. Okay. Put the Riemann. Oh, you're talking about the Riemann hypothesis, right? Okay. Good. Someone will do it and then say easy 90. I see. I get it. I'm up to speed. Good. I do like the Enrich website. They recently changed all their branding. It's now very blue. It now says University of Cambridge, slightly larger. I always ignore the age range and the challenge level. I think this problem entertained a room of non-mathematicians and mathematicians and top-level cutting-edge number theory researchers for some time, and the questions they were asking each other were not 1 star, and all of them were over the age of 16. And if it entertains them, it's enough to entertain us as well. Maybe that's the message, more than anything about the t-shirt itself. The idea that sorting problems into age ranges and challenge levels doesn't mean you can't still have fun. They've put the unsolvability of the quintic on Enrich somewhere. Ooh, should we try and find it? Let's try and find it. Let's try and spell quintic. Well, I've not found it, but I have found an introduction to Galois theory. History. Who wrote this? Dan Goodman. In 2002. Okay. Oh, groups and fields. Yeah, there's a lot of stuff that we did on a stream one time. Field extensions. Oh my goodness. Sure. Yep, okay. This was pretty good. Yeah, this is exactly what you want, isn't it? Oh my goodness. This is more than an introduction, isn't it? Oh my goodness, just go for it, go for it! Here are the steps. 3rd, you proved that the Galois group. Hard to pipe by a long, long way. Not going to attempt what a soluble group is. It would take 40 hours of live stream. 4th, you proved that it's not soluble. That's not too bad. 5th. Okay. It's the small step at the end. I remember this. Yeah, cool. Is this what you mean, Lord? 60 minutes. This is a lot. This will keep you busy for a long time. Right. Okay. I'm going to call it there, I think. We've all got things to think about as homework or whatever. We've got Fibonacci numbers. This looks a bit hard. We've got an introduction to Galois theory. This looks very hard. And we've got a weird function that takes the floor of n root 2 times n, which Vicky Neal did some research on. We've got matrices of Fibonacci numbers at the same time. Good. Here's a cool article. Should we put a link in chat? Put a link in chat. Galois theory. Done quick. GTDQ. Right, good. Okay, wrapping up, I think. I haven't told you the answers to questions that I took to a party, so I missed last week because I was at a party. People in chat gave me questions to take to my friends. I haven't collated the results together, so we'll do that another time. Maybe on the Thursday show, maybe on the Sunday show. Yes. Oh, is chat ahead of the video? I guess that does make sense. Yeah. Chat's ahead of me. So you get the message from James, and then, yeah, and then James does some typing. Yeah. I'm from the future, but also I'm from the past. I did the survey of people's favourite numbers. the results will shock you. They surprised everyone at the party. So, brilliant. Right, good. Okay. Things I have outstanding. We always do a to-do at the end. Oh, this has stopped working. Because we've been looking at prime numbers. Okay. Connect it. Accept it. No. Not happening. Today we have looked at Fibonacci numbers, links to matrices. We've been going upstairs with the Fibonacci numbers. We've thought about the Fibonacci numbers a tiny bit, and other numbers are available. We had a quick diversion into complex numbers and matrix things, talking about the sum of two squares and the sum of two not squares. And what's scribbled? The restriction was numbers between 1 and 10 for your favourite, and then least favourite overruled was the separate question. I think I did between 1 and 10, I think, to make it easier for the voting. At some point. Results. Good, right, I should work out how to close that poll. 7 came back for a vengeance. Yeah, okay, let's do this mini result now. The winning number was 2, which doesn't make any sense to me. We said whole numbers between 1 and 10, and the most popular, by far, was the number 2. Nonsense. Absolutely crazy. And then everyone was really kind of upset and shocked that, exaggeration, but everyone was surprised that other people had picked 2. It's a good number, but what? Yeah, pretty weird. Made me think my friends are weird. Then I remembered that I'm the one who does Sunday live streams. Thanks for watching. No, hang on, I want to fix my... I've just noticed. I want to fix this. No. Yep. Yeah, nailed it. Why is it always like that? Thanks for watching. I'll see you like take away their devils. See you next. Sorry, is that 2 exclamation marks because you're doing a double factorial down to, because it works, right? Yeah, here we go. Matter is in a field of characteristic 2, so for them 1 plus 1 is 0. Wait, factorial. So 1. So they're in a field of degenerate field. Okay, right, enough. See you next week. Yes. Bye.